long. So it's more fun than just kind of talking very boringly about numbers on the screen if we actually try to engage another bite's worth of folks. Can I ask for your indulgence one last time to have 8 people join us up here? OK, you are number 1. Come on up. Number 2, 3, 4, 5, 6, 7. And really, it's just me and the orchestra today. OK, well, it's, wait, I said 7? How about let's go in the back there? 8? All right, come on down. I think I got 3, 4, 5, 6, 7. Perfect. All right. You raised your hand first. So go ahead, if you would, and just line yourselves up on stage in a manner consistent with the sample on the screen there. One, two, three. Oh, there we go. Just in time. All right, and so that the lectern's not in the way, why don't we come over here, if you don't mind. All right. So this is the easy part. Make yourselves look like that. All right. Hopefully we are correct. OK. So now we need 1/9 volunteer. And this person actually has to do some thinking on their feet. OK. Come on down. Yep. In the black shirt. Oh, I'm sorry. We'll get to you next time. Black shirt. How about? Come on down. All right, so in just a moment, we're going to have to figure out how we can take this array of numbers, which is effectively random, much like the first array that Sean actually used, but we need to sort this. And even though this, too, might seem at first glance, and this is kind of easy, right? Like there's number 1, let's put 1 there, 8 there. That's the sort of human approach, where you just kind of get an overarching sense of things, and you just kind of know instinctively what to do. But again, if you're a computer or even a robot, if you think of it that way, you really can only do one thing at a time. And so you might have to first look here behind this door, and there's a number. Then you can move on to the next, then on to the next. But then if you want to swap people, you actually have to spend some CPU time, some CPU cycles to move them around. So again, we come back to this notion of swap. But unfortunately, according to last week's buggy program, swap doesn't really work in C. So that's something else we'll have to fix before long. And what is your name?
Casey.
Casey, OK. Casey, David. So Casey is going to be our sort of godlike figure here and actually moving these folks around. So if you guys could take just a step or so back, just so Casey has some leg room in front. This may end up being a little awkward. But let's do this. So Casey, your task first is to sort these people. And before you actually instruct them to do something, at least give us, the audience, an idea verbally of what you're going to do. What would you like to do? Sort these people. What would you do first?
In a ascending order?
Yes. So from 1 on the left to 8 on the right. How would you approach this problem as a normal human being?
I would find 1 and move it all the way to the right.
OK. So do that step. Go. Very good so far. OK. What would you do next?
I would move number 2 next to number 1.
OK. And next?
Number 3 over here.
OK. So there's a pattern.
Number 4 is already in order.
Good.
Number 5 between 4 and 6.
OK.
And 7 between 6 and 8.
OK. Done. So this looks correct. Oh, very good. Very well done. So the question, though, for the audience is, how long did that take? Not so much in like seconds on a clock, but how many steps, how many operations, how many units of time? Like, how can we begin to quantize what we just did? So n-1. So it felt like if there's 8 people, right, she had to do 8 things minimally. So there's at least 8 steps. But it's not quite as simple as that, right? Again, if you now think of these humans as an array, each of them in their own bucket of memory, albeit side by side, but in a distinct location, how did Casey actually find the number 1? So let's actually rewind. So Casey, you could come back here. If you guys could revert back to the original configuration. Let's now dig a bit deeper, because sorting n people is actually not as fast as big O of n steps, or even n-1. That did not take n steps. We actually have to push a little harder on this question. So again, we rewind, and you said, OK, you're going to pluck out number 1. How did you find number 1?
I looked at all the numbers, and from left to right, I found number 1.
OK, good. So reasonable human would do that. You kind of look at all the numbers. But therein lies a hidden cost, right? How do you look at all those numbers? Well, even if your brain did it super fast, what you probably kind of sort of did was at least glance at 4, glance at 2, glance at 6, glance at 8, glance at 1. And then maybe there's a 0. So you might have glanced at 3, glanced at 7, glanced at 5. And then you concluded that number 1 is indeed the smallest. So how many steps did we actually just spend? That was actually 8 steps to find the smallest number in this array. And so then what did we do? So now let's fast forward. So you identified number 1 n steps later. How did you move him over here?
I told him to move.
OK, so you told him to move. But now let's consider that. How does this work? So what's your name, number 1? Sendash. So if you could go ahead, step forward. And no one else moved just yet. How did you go about inserting yourself into the right part of the list?
I just walked to the end.
OK, so you walk to the end of the list. So let's keep playing. So do that. Yep, we'll do exactly what you did last time. And then we'll pause you. Pause. Now what did you do?
Stop.
Thank you. Stopped. OK, and then what? Now, if this were an array, what did we just do? We tried to plop number 1 in location negative 1, right? You can't just kind of go to the beginning of the array. You wanted to go at location bracket 0. So, and what's your name, number 4? Sam. So Sam, what really should Sam do here? And what should number 2 and 6 and 8 really do? You know, it'd be nice if they kind of made some room. But wait a minute, what did that just cost us? That's 4 more steps, right? So that's expensive. Well, let's rewind. That feels too expensive. This is taking forever now with all these steps. What's slightly smarter than having all of his neighbors move down? OK, so just swap who? So how about just 4 and 1, right? Because Sam here, yeah, he's number 4, but we don't really know anything about him yet. He might be the biggest number. He might be the smallest. So far as we're concerned, Sam is still completely random. So who cares if we put him in another random spot? So let's move Sam over there. That frees up bracket 0. So now Sendash can go into bracket 0. So now you can, yes? So now how many steps did that take? Well, to rewind, it first took Casey some 8 steps to identify number 1. Then it took, what, 1 more step to move Sam, and then 1 more step to move Sendash into that spot. So that's like 10 steps. So it's like n plus 1, n plus 2, give or take. But it's at least n, give or take. So Casey now, and this story is obviously taking a lot longer now, what do we do next to find number 2? Or rather, the next smallest?
Look at them again.
OK, so we look at them again. Do we need to keep looking at all 8 people, though?
No, you can skip the first one.
OK, good. So there's this slight optimization here, right? We don't need to look at spot number 0 ever again where the number 1 is, because we just put him there as the smallest. So we can at least whittle this down to a problem of size n minus 1. Then next, n minus 2, n minus 3, dot, 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 hopefully down to 0. So how do we find number 2? What is your name?
Emmy?
Emmy. So Emmy happens to be holding number 2, but do we know she's the next smallest? What do you think? Casey, how do you know for sure or not if Emmy is the next smallest value?
I've already looked at all the numbers.
OK, so really, even though it looks obviously 2 is pretty small, it's probably next to 1, we only know that if we look at a total of 7 numbers. And now this is getting a little awkward up here, right? So let's just fast forward verbally. So now to find 3, we do n minus 2 steps, then n minus 3 steps, then n minus 4 steps, until finally we find number 8, and we can just leave him in spot number 8. So that then begs the question, how many total steps was this? It does feel like it was way more than just the initial sense of n steps, or n minus 1, to sort all these people. When you actually start counting up the comparisons and the swaps, so really, how many was this? Yeah, so if you actually add all this up, this is effectively n steps plus n minus 1 plus n minus 2 plus n minus 3. And now if you kind of think back to like your high school physics book or math book with all the formulas and whatnot, this is a series of sorts, a summation. And so if you actually add 8 plus 7 plus 6 plus 5 plus 4 and so forth, you essentially get that formula n times n plus 1 over 2. So n squared something. So in short, it is in fact something like n squared. And again, if we added all these up, that would be the formula we get, n squared something. And how do we feel this? Well, just to, if you'll humor me with this part, how do we go and find number 3? Well, you go here, here, here. OK, so smallest 6, not smaller. Smaller 4, oh, smaller still 3. So you can kind of feel the inefficiency of this. If I now pluck out 3, swap him with 6. Now I can at least optimize. I never again have to look over here, but now I start with 8. Is 8 the smallest? At this moment it is. How about 4? Ooh, 4 is now smaller. 6 is not. 7 is not. 5 is not. So I better have remembered that 4 is there. So I pull Sam out, swap with 8. So in short, even though this went super fast the first time, if you really break it down into sort of scratch puzzle pieces or C loops, well, really what Casey would have been doing is walking this far the first time, then going back, starting here, walking here again. So this is 7 steps. Then we go back over here. Now we've got 6 steps. Now these are real steps. Because arrays are contiguous back to back, we do have random access, right? I can go from bracket 7 to bracket 0 like that, because I know exactly where 0 is. But if I want to compare these people, I can go back here very easily. But again, you're literally going back and forth and back and forth and back and forth, and that adds up. And in fact, it gives us something like n squared. Let's do something a little different. So if you guys could reset one last time to this original configuration. That felt nice, but it turns out we can solve this problem actually in like at least half a dozen ways, some of them increasingly powerful or even slower. So let me just do this. That was perfect implementation. In fact, what Casey proposed is something called selection sort. There's a whole bunch of algorithms the world has invented. Selection sort is the one where literally you select the smallest number, then you do it again and again and again. And just by common sense, if you keep selecting the smallest number, you're going to get a sorted list if you do what Casey just did. There's this other one, though, called bubble sort. And this one you can kind of see, as the name implies, that there's a bubbling effect. So let's actually try this. Let's compare each of these volunteers side by side. And if they're out of order, let's just swap them pairwise. Let's see if we can take a whole different approach here. So Casey, we point first at bracket 0 and bracket 1. Are they in order or out of order? Out of order. So we swap. So that took what? 1, 2, 3 steps, maybe, right? 1 step to compare, 1 step to move Sam, and 1 step to move Emmy. So that's like 3 total steps, but that's constant. So that's nice. One big 3-unit step. All right, so now we compare 4 and 6. And do you want to swap or not?
Don't swap.
OK, 6 and 8.
Don't swap.
8 and 1.
Swap.
So that's 3 more steps we just spent. 8 and 3.
Swap.
8 and 7.
Swap.
8 and 5.
Swap.
Done, right? All right, so not quite, right? This algorithm's a little different in that we did fix some problems along the way, right? We fixed a lot of juxtapositions where we fixed the ordering. But what is the worst case scenario when trying to sort n humans like this? And what's the worst possible input? Right, they're in reverse order. So let's actually see what bubble sort's like in the really the worst case. So let's ignore this now, and now go ahead and just line up in reverse order, 8 to 1, and let's feel how much faster or slower this alternative algorithm is bubble sort to that thing called selection sort. So here we go. Bubble sort begins with 8 and 7, 8 and 6, 8 and 5, 8 and 4, 8 and 3, 8 and 2, 8 and 1. OK. So done, but not quite. What's curious about bubble sort, and if you actually kind of think this through logically to the end, this will actually work. Because if you just keep going back and forth, fixing all of the problems, albeit slowly, they will eventually bubble up the small numbers here and bubble down the big numbers there. And that's where bubble sort gets its name. But how many steps did this actually take? Well, in the worst case, number 8 was indeed over here, and number 1 was over there. So how many spots did number 8 need to move to fix just him? He had to move all the way from the left to all the way to the right. So that's like n steps. It's actually n minus 1, but it's like n steps. What about the next person? Now we have to move 7 all the way down. That's n minus 2. Then we have to move 6, n minus 3. Then n minus 4. So where is this going? What's the running time of bubble sort? It's also n squared. Why? Well, there's n total people up here. And on every iteration, you might move someone into their perfect position, but you still have 7 more people, then 6 more people. So you have to do n things, roughly n times. And so even if we don't really do out the math, but just think about it, you've got n people, and you might have to walk this list n times to fix all of the juxtapositions, all of the misorderings. That's n times n, or n squared. So bubble sort sucks. Selection sort sucks. Like we saw the graph up there before where linear was good, n over 2 was good, logarithm was amazing. But now where are we at? We're at the n squared, which is this curve that goes off into the positive direction and is actually pretty darn slow. So can we do better? Well, first of all, a round of applause if we could for our volunteers here, and Casey in particular. Nicely done. you want to just exit there, you can keep the papers as souvenirs. Let's see if we can't see or feel now some of